Hello everyone, welcome to this exam question revision on acids, bases and pH, suitable for OCRA, possibly other exam boards. Okay, let's cracking with this. A buffer solution is based on methanoic acid, Ka given, and methanoate ion. This is a 1 mark question, by the way. Right. In the buffer solution, methanoic acid concentration is half of this concentration. What's the pH of this buffer solution? 4 choices given. Possibly you take an hour, a minute and a half to answer this. Anytime during this video, if you feel like you feel confident, you can pause the video, try it for yourself, and then continue the video and check. I will ask you to pause from time to time when it's appropriate. Okay, I think it's a good place to start is a Ka expression like so, and as it's given here. Ka is there. We have the concentration of the acid is half as much as the conjugate base or the conjugate ions concentration. Okay, conjugate basis concentration. Okay, so I have fixed that as 1. So instead of the A minus, I put that as 1, and this acid concentration should be half of that, so I put 0.5, so you get the ratio correct. Okay, then we have we need the H plus ion concentration for the pH, right? So we multiply Ka times 0.5 divided by 1, and that should give us half the Ka, right? So you have the Ka value here. Okay, so you just put that in. So if I multiply Ka by 0.5, I get 8.5 times 10 power minus 5, right? So for I've got the hydrogen ion concentration here, and I just have to do pH equals minus log of that value. That gives us 4.07. So must be this D is our correct answer. Let's have a look at this question here. Although this is a 1 mark question, this gives us a perfect opportunity to explore and learn sideways a little, recall some ideas here. Okay, so this gives the equilibrium. Water can ionize into H plus and OH at any concentration of at any temperature. This is true. H plus and OH minus ions are always present in water. Okay, so keep that in mind. Kw is 10 to the power minus 14. Is this true for any temperature? This is not. 100 degree, you just need to know that it is just not, this is temperature dependent. This is like K, the equilibrium constant. As you know, K equilibrium constant changes with temperature. Even with that simple idea, you should be able to say this is not the correct answer. Okay, so but however, it gives us an idea, it gives us an opportunity to look into this as well. What is the Kw? That is Kw, right? At 100 degree, it actually goes to this value. Now, if you work out the pH at around 28 degrees C, which is the standard temperature, this gives us, even 25 degrees C, that gives us a pH of 7. Okay, so if you do the log of this, that gives us pH of 7, right? So keep that in mind. 100 degree, that the K value itself increases to that. Okay, so that gives us a pH value. If you do the minus log of this, that gives us 6.14. Now, this is weakly acidic, right? But at 28 degree, you would consider that as weakly acidic water, right? But it's not actually, because the concentration of H plus is exactly equal to OH at any temperature. That's what this is, right? So H plus is equal to this. This is the correct answer. Now pH, as you know, it's not 7 at any temperature, as you can see for yourself, so this can't be true. pH is 6.4. so from just considering this, you can pretty much rule out many things. Okay, so you need to have some idea about this equilibrium constant is temperature dependent, Like all equilibrium constants are temperature dependent, right? So higher temperature, K value changes depending on whether it's exothermic or endothermic, of course. Okay, the solution contains only H2O. No, this is not true. It always contains H plus and OH, right? So that is not true at any temperature. Right, so what other thing that you can explore in this? Yes, this equilibrium, the K value increasing, the K value is increasing from here, 1 times 10 to 2, this shows that the forward reaction is exothermic. So at higher temperature, there is shift to the right hand side. So this shows delta H for this forward reaction must be positive value. Okay, it's endothermic. Positive, know what value it is, but it's endothermic. Okay, so the forward reaction is endothermic. That's what it is shown. So this is another thing that you can consider and keep in mind. Maybe it comes up in another question, right? So this also helps us to learn a little bit about this, and also to rule out many of this, rather than just saying, okay, that's the correct answer, that's wrong answer. We can actually think a little bit about that. Okay, this question is a definition question. It's asking what's a Bronsted-Lowry acid and a weak acid. Partially dissociates, that's a weak acid. Bronsted-Lowry is a proton donor. So this, make sure that you don't know the definition. You know the definitions, okay? There you go. H plus, it's a proton donor. That's a Bronsted-Lowry acid, okay? Weak acid partially dissociates or ionizes. Okay, so we did practice this in first video, part 1 of the acids and bases and pH. So go back to part 1 if you're not sure about this. Okay, now I'm not going to explain this, I'm just going to solve this for you, right? So that's your it's a weak acid. Phenol is a weak acid. Okay, as you can see here, it's actually proton, donating that proton, right? You can see that's lost the proton, so this must be the acid 1. So label that as acid 1, go straight to the other side, and the conjugate base is the base 1. Okay, then if you got acid 1 here, on this side you have to have an acid and a base, so this must be acid 2. Like I said, if you're not sure about this, go back to video 1 where we have where we actually looked through this. Okay, so this must be base 2. So you identify the acid-base conjugate pairs like so. Okay, so in this question, notice we have the concentration of phenol given in gram per dm cube, and we need an expression for the dissociation constant Ka of phenol. So you have to be careful. You have to actually write the phenol's formula. So you need to have some idea about how phenol looks like organic chemistry, right? C6H5OH is phenol, and that dissociates like this: C6H5O minus plus H plus. Actually, you got this from the previous part over here. So you got some, yeah, you got it here. Okay, so you got that, right? So that you can write the Ka value fairly easily, right? So you just write, so there you go, that's Ka equilibria for this weak acid. And for weak acid, we know that concentration is equal to that one, so that's what we're going to use. Unlike the question before where we looked at buffer, we have the different concentration of this and this. We don't have that here. This concentration of the conjugate base is exactly the same as that, because the concentrations are equal for a weak acid. So you can write, instead of that, you write H plus square, because we're interested to find hydrogen ion concentration. So instead of this, because you can rewrite that as H plus square, because that is exactly equal to that one. Okay, so now you got that, and when you rearrange that for H plus square root of that, that's a standard way of calculating hydrogen ion concentration for a weak acid. You just put the numbers in. So you convert 4.7 gram into moles, because we want the concentration in mole per dm cube. That gives us so just divided 4.7 over here by its formula mass of phenol, that gives us 0.05. This was the mass present in a liter, so this is the concentration in mole per dm cube. So we got that concentration, we just have to put that here, okay, over here. So 0.05. now we have to put the Ka value as well here. So that is oh, we need to find the Ka, right? Now we have the Ka value here. We need to find it. It's there. Okay. Oops. Okay, so Ka is 1.3 times 10 power minus 10 times 0.05. Okay, so if you work, okay, so substituting the values of Ka and the concentration of phenol, you get this 2.55 times 10 power minus 6. So we have got the hydrogen ion concentration. I suppose you know the next step is like minus log of this value. So minus log of this value here, do that in your calculator, you will get 5.59. Always give the pH value to 2 decimal places. Okay, take a moment to read this question. It's a bit wordy here. Student needed to prepare a buffer solution with a pH of 8.71. And we have the Ka value for phenol. Okay. The Ka value for phenol. Student used 0.2 mole per dm cube of phenol mixed with equal volume of sodium phenoxide. Okay. At any point during this question, feel free to pause and try for yourself. Use your knowledge in buffer solution to determine the concentration of sodium phenoxide solution that the student would need to mix with the 0.2 mole per dm cube of phenol solution. Now mind you, you need to pick up these points. Equal volume, right? So equal, so bear that in mind, equal volume, important thing, of sodium phenoxide. The volume should be the same. Okay, so what this means is when you take some solution of phenol, and then you have to have the equal volume, and when you mix them together in a bigger beaker, so this is twice the volume, but the concentration goes half. So if this is phenol, C6H5OH, it's at 0.2 mole per dm cube. When it's mixed like so, its concentration now becomes 0.1 mole per dm cube. So that's something to consider. Also you have to bear in mind that this when you find the concentration of sodium phenoxide, that is the concentration in this mixture, not the original phenoxide. So let me write phenoxide here. Okay, so this concentration of sodium phenoxide, you have to find how much what the original concentration of sodium phenoxide is, sodium phenoxide is, but after mixing is what you can find with the help of Ka. Ka only gives you the concentration of phenoxide, the conjugate base of phenol in the mixture. Okay, so we can write Ka like so for phenol, like we done in the previous part. From the pH value that you're aiming to get, 8.71, or the student is aiming to get, you can actually get the hydrogen ion concentration. Okay, so from the Ka value, and also we now know the hydrogen ion concentration by doing this 10 to the power minus 8.71. From the pH we know the concentration of hydrogen ion. Now you want the concentration of sodium phenoxide. Okay, use your knowledge in solutions ammonia. Determine the concentration of sodium phenoxide solution. that the student will need to mix, right? So we need to know the sodium phenoxide in the mixture here, not the original solution here. Okay, we're just finding the concentration of sodium phenoxide in that mixture. We're using Ka value, which is here, there. Ka equals 1.3. So I'm going to substitute the numbers over here. Okay, 1.3 times 10 power minus 10. Okay, that gives us so just working out the phenoxide concentration in the mixture, that gives us 6.66 times 10, or 667 times 10 power minus 3. Now this is the concentration in the mixture, so the original concentration should be twice as much, because we are using same equal volumes of both these solutions, right? So you need to multiply that by 2. That gives us this value, 0.0133. I'm going to put this to 3 significant figure. That's it, 0.133 mole per dm cube. I multiply this by 2 because of this reason. We found the concentration of the sodium phenoxide in the mixture, and because we're using same equal volumes of this, it has to be multiplied by 2. I hope that makes sense. Mind you, I looked at the mark scheme for this. It's giving it's been given as 0.13, but I checked, this must be some error in the mark scheme. So although this is an exam question, this was part of this initial question paper, the specimen papers. So it must have been a mistake, but you can check the calculation again. I'm getting 0.0133. Take a minute to read this carefully, underline any key points here, and then pause the video. If you think that you can do this yourself, that'll be great, or just keep running, pause, and then check. If you want to do it, then check the answer key, then play again. Okay, so some biological activity can be reduced by increasing the pH, making it alkaline by adding calcium hydroxide solution to the sewage water. In all parts of this question, assume that the temperature is 25. A chemist checked the concentration of aqueous calcium hydroxide in the sewage water by titrating with this concentration of hydrochloric acid, right? That's the equation. The chemist titrated 25 centimeter cube of sewage water with hydrochloric acid. That is the volume of hydrochloric acid used. Okay, right, and then to the end point, calculate the concentration of the calcium hydroxide in the sewage water. Okay, do we have the concentration of hydrochloric acid? Yes, we have the volume of hydrochloric acid. It's so easy, it's not even pH yet. Okay, so you can actually work this out yourself. Okay, so first calculate the moles of the hydrochloric acid used in the titration by multiplying the concentration, that's the C, with the volume. We get the moles of the hydrochloric acid. So the moles of calcium hydroxide would be half of this, because of the equation it shows 2 moles, 2 to 1 ratio. To work out the moles of calcium hydroxide, divide that by 2. So that gives us 5.34 times 10 power minus 5. Now we're going to work out the concentration. So we got the moles, we got the volume. Without running out of space, I'm going to put that here, because the concentration of the calcium hydroxide would be N over V. Okay, and we have used that much sewage water, right? Oh, this is the number of moles in 25 centimeter cube, and we need the concentration in a liter. Okay, so moles divided by the volume of the calcium hydroxide actually used, which is the sewage water, 25 centimeter cube, which contains the calcium hydroxide. It gives you 2.136 times 10 power minus 3 mole per dm cube. Now we are getting into the pH part of this question. This is a base, not an acid. So we have the concentration of this calcium hydroxide. Okay, so we have this question which deals with the pH of the calcium hydroxide solution. We are given the concentration of calcium hydroxide, which is that it's a base. So it's better and easier to use this ionic product of water, H plus OH minus this, and then we need the pH, which means we need the hydrogen ion concentration. That's what we need to calculate. So you have to use the ionic product of water, 1 times 10 power minus 14, divide that by the concentration of OH. We don't know the concentration of OH, but we have the concentration of the calcium hydroxide. Mind you, each molecule contains 2 OH minus ions, so you have to multiply the concentration of calcium hydroxide by 2. So now you just have to put the concentration of OH minus ion into this hydrogen ion concentration. So I'm going to 1 times 10 power minus 14 divided by that value, 5.4 times 10 power minus 3. And then if you put these numbers into the calculator, we get 1.85 times 10 power minus 12. So now you do so you want the pH. Now you got the hydrogen ion concentration, you just have to do that minus log of the hydrogen ion concentration. That gives us 11.73. It's the pH. Okay, so after further treatment, the water could be used for drinking. The drinking water produced the OH minus ion concentration 100 times greater than H plus ion concentration. What's the pH of the drinking water? Okay, now so go back to your original KW equation, right? Because this is what contains both H and OH. We know that this is 10 power minus 14 at 28 degrees C. Now we have this condition, OH minus concentration will be 100 times this. So instead of OH, I'm going to write 100 times this. Okay, H plus times 100. Okay, so instead of OH, write 100 times H plus. That allows us to solve for, now we need to find the pH, right? So that allows us to solve for H plus. So now I can write H plus square equals, take this down here, 1 times 10 power minus 14 divided by 100. Okay, so I have the hydrogen ion concentration squared equals this. Now I want the hydrogen ion concentration, take the square root of this. And that gives us 1 times 10 power minus 8. pH would be minus log of that. That gives us 8. Okay, so take a moment to read this question and then pause and read. Okay, I'm going to carry on. So if you read this question, it's got, when dissolved in water, calcium phosphate dissolved. So you have this fertilizer, calcium dihydrogen phosphate. Okay, this compound, one of the world's most important fertilizers. When dissolved in water, it forms this ions which is taken up by plants really easily through the roots. H2PO4 phosphate is really phosphorus is useful for plants. So that's a good fertilizer. The question is this is a 1 mark question. You have to write a balance symbol equation. I think the pH is coming up in the next part. So calcium dihydrogen phosphate is produced by, this is a product, so you write that as a product here, produced by treating rock phosphate, that over here, treating with sulfuric acid, that's there. So you just have to look carefully as the missing species, right? So phosphate twice is here already, H2 times 2, so you have 4 hydrogen here. So you might as well start balancing this and look for what's missing from this, right? So put 2 here, try 2. That means you have 2 sulfate ions now left. you have one calcium already used. So let's try the 2 calcium left over here, right? So let's say yeah, so it must be like this: calcium SO4. Oh, calcium SO4. SO4 is 2 charge, so I'm going to remove that bracket. So that's it. I just tried to balance this by putting the 2 because you have 4 hydrogen here, so I tried to make that into 2. That means 2 sulfate is left, 2 calcium is left, so that the only possible other ionic compound is 2 calcium sulfate. Okay, so that is asking you to write a balanced equation for this. Done. 1 mark. Okay, so write an equation to represent HPO4 minus. It acts as a weak acid, represent the dissociation of H2PO4. So it's a weak acid that must be donating a proton, so write like so: PO4 minus, okay, minus, remember the equilibrium sign because it's a weak acid. So what's left after, so put H plus, going to donate H plus, so what's left is HPO4 minus 2. Remember the state symbols, and that's aqueous, or you can also write the 2 hydrogen ions forming from this weak acid, or this ion actually. So H2PO4, same aqueous, minus, giving 2 H plus ions, and what's left is the PO4 2 minus this time. Okay, so 2 hydrogens lost from here. There is already 1 minus, so this should be 3 minus. Okay, as you can see, 2 hydrogen ions have lost, so that means each hydrogen ion lost will make this 1 negative. So it's now already 1 negative here, so this must be 3 negative. The conjugate base of H2PO4 is just this one, HPO4. After losing that 1 proton, it's got that. That is the conjugate base of that acid. This is asking for conjugate acid. Just add, for conjugate base you take away a proton. Now this time you add a proton, so that means you will have H3PO4. That negative charge will go because you've just added a H plus to this. Okay, so part 3 of this question, we've seen the solution of calcium hydrogen phosphate in water acts as a buffer solution, right? So just with the aid of the equation, how this buffering takes place. Now we've already seen in the previous part, this in water produces these ions which can act as either acid or base, H2PO4 minus. So this can either accept an acid or alkali, right? Perfect for a buffer. So any added H plus ions will be taken up by this ion, right? So how does it work? So we just answered this in the previous parts. All you have to do is make that into a buffer equation, right? So this, when you add a H plus ion, becomes H3. Oh, I should use an equilibrium, right? Reversible symbol there, right? Like that. Okay, H3PO4. That's it. So this is when adding small amounts of small volumes of H plus, small concentration of H plus changes. As you know, buffer can minimize changes to the pH if you add a small amount of H plus or OH minus ions. So this does it like that. Okay, so mind you that the top one is when you add a H plus ion. When you add a OH minus ion, this behaves as an acid, so it donates a H plus ion to this, and you get water and the remaining ion. This is already 1 negative, so this becomes 2 negative after one of this proton is donated to the OH. Okay, so another exam question on pH. Nitric acid. This is a strong acid. Sold by a chemical supplier, 65% by mass, has supplied each cubic decimeter of this nitric acid as a mass of 1400 cubic decimeter per dm cube. Okay, so per liter. It's got this much mass. So you just have to convert that to, first of all, find the concentration of the nitric acid. Okay, so to visualize this, we have nitric acid, this from a chemical supplier. 1 dm cube weighs that much. That's what this question is telling us, right? So far. And then out of this, 65% will be the nitric acid. Okay, so let's work out the mass of nitric acid by just working out what is 65% of this. That gives us 910 grams. Okay, we get this number of moles, 14.44. It's already in each cubic decimeter. That is the concentration. So we have that many mole per dm cube, right? So now we have the concentration of a strong acid. Remember, for a strong acid, we just take the concentration of this. That is the concentration of H plus ion. But check if it's monobasic. So one acid only produces one H plus. So now you just have to do minus log of the hydrogen ion concentration, which is this. For a strong acid, that's true. So that gives you, okay, so that gives us minus 1.1597 or to 1.1 minus 1.16. You may be wondering, can pH be minus? For very strong acids, that's what we get. Okay, here's a 6-mark question on the blood equilibria and the buffer system that's present in the blood to actually maintain a healthy pH of 6.38. So H2CO3, so look at the information really carefully, take a moment to read it carefully. Okay, so what is given here is H2CO3 is a weak acid, first of all. It's a weak acid, okay, together with hydrogen carbonate ions, which is its conjugate base. You can see that straight away. Acts as a buffer to maintain pH of the blood. pKa value of the carbonic acid is given. So from this we can actually work out Ka, right? Explain in terms of equilibrium how the carbonic acid mixture, hydrogen carbonate mixture acts as a buffer to in the control of blood pH, and calculate the ratio of the ion to the acid in the healthy blood. So it's a 2-part question. So let's deal with how it acts as a buffer first. Okay, so it's always useful if you're given a weak acid, write as an equilibria and think of it in a simple way or just look at the H plus ion, what happens to it. That's the easiest way to explain this. HCO3 minus. Okay, so if you increase the H plus ion, so in a buffer system, it actually minimizes the change in pH with the addition of H plus. Small volumes or small concentration of H plus increase will not affect the pH that much. It minimizes the change. Or OH minus. So you add any of this, it keeps the pH change to a minimum. How does that work? It shifts the equilibrium one way or the other. So imagine the first case where you increase the H plus ion, so that is increased. That shifts the equilibrium to the left. Okay, so if you increase this, shifts the equilibrium to the left, because, and then you can think about, okay, that will minimize according to Le Chatelier, right? So then the left equilibrium, if it was to go that way, it has to react with the HCO3 minus. So the added H plus ion reacts with HCO3. There is enough concentration of HCO3 in the blood, so that reacts with the H plus ion to produce H2CO3. Okay, as you have a high concentration of these two, but we'll work out the ratio. High concentration, both of them, so it does not affect the change in concentration, doesn't affect the pH that much, right? But the added H plus being removed, right? You don't have to write all that, you just have to write that expression and say any increase in H plus makes the equilibrium shifts to the left. That's one point that you have to say. And then you have to say you can say it reacts with HCO3 to go to the left. Okay, now let's look at the other scenario. When you increase OH minus ion, that will react with this H plus ion to bring it down this time, right? Now this time around the equilibrium shifts to the right, okay, to minimize that change, because you're reducing this concentration, that equilibrium will shift to the right this time. Okay, now when that happens, then you can explain, okay, what might happen here. Okay, so this is the easiest explanation. This H plus ion reacts with OH minus ion to cause that shift. Or you can say H2CO3 as acid, that reacts with the added OH minus ion to produce HCO3 minus that ion, plus it produces H2O, because that is H plus is being donated to that and this, right? Slightly harder explanation, but I think if you can explain with this equilibrium, that's good enough. So when the H plus ion that reacts, H plus reacts with the OH minus ion, that goes down, equilibrium shifts to the right. Okay, I think you should also consider the mark scheme, things that been said, what's allowed, what's not allowed. Take some time to look through this. This is the only explanation I have given, that's good enough. Increase in H plus addition reacts with the HCO3. Increase in H plus, so you first of all start off with that equilibrium and then go ahead and say reacts with H plus and to produce this, right? Okay, so consider this equilibrium. H plus, if you increase, the equilibrium shifts to the left. So that's one mark for saying that. And for that to shift to the left, it has to react with HCO3, which is what the mark scheme states here. H plus plus HCO3 giving H2CO3 shifts to the left. Okay, I think it's much easier to think of just in terms of this H plus. You increase that, it shifts to the left. Now decreasing, adding OH minus ion shifts to the right. Okay, that's because it has to react with the H plus ion, okay, to bring it down. That's the easiest explanation. Okay, increase in OH will lead to H plus OH, right? So that's the easiest explanation. Or you can say it reacts with that one to shift it to the right. Okay, so make sure that you have 2 points there: equilibrium shift and which species it reacts with. I suggest that you just talk about the H plus ion. Okay, so let's have a look at the second part of this question, which is asking you to find the ratio of the conjugate base to the acid, right? So start with pKa value given here. So find the Ka value from this by doing 10 to the power minus 6.38. Remember, pKa value equals minus log of Ka. So from that we can actually work out Ka like so. So we've got the Ka value. You also have the pH over here. That gives us the hydrogen ion concentration, right? So let's write the Ka expression first of all, which is H plus HCO3 minus divided by H2CO3. Okay, right. So we have the hydrogen ion concentration by doing 10 to the power minus 7.4. Okay, so I've got the Ka expression. Now I want to know the ratio of this conjugate ion to this. That's what the question's about, right? So you got this ratio. If you rearrange this, keep the Ka to this, so keep these two on one side, the ion to this acid. I think I've made a mistake here. Let me just change that to Ka. So that has to, hydrogen ion concentration has to be in the denominator. Okay, H plus ion concentration, right? So now we have to just substitute these values for Ka. So basically I have kept this ratio on one side because that's what we need to find. So keep that and rearrange it so everything else is on the other side. So that's Ka divided by that value, H plus, yep. So Ka value is over here, 4. So it's over here. Okay, that's Ka 4.1687 times 10 power minus 7 divided by the concentration of H plus, which is here, 3.98 times 10 power minus 8. It's useful to safe to put the brackets on when you do this in a calculator. All right, okay, so take a moment to look at the calculations as shown in the mark scheme, as well in a way you get the marks, which steps get the marks. Okay, let's have a look at that. Pause the video if you need to. Okay, here you have been given some information, so take a moment to read this. Student investigates the reactions of two weak monobasic acids. So monobasic both are, so one proton donated by both acids, right? This one, that one. Student wants to prepare a standard solution of 2-hydroxypropanoic acid, which is that one, right? 2-hydroxypropanoic acid is a pH, and the student wants the pH of 2.19, right? Okay, so keep that in mind. In useful information given, you want the pH of that. Okay, and the volume 250 centimeter cube of standard solution from solid. Okay, so you have to weigh this, you need the mass. But it doesn't say ask for mass, it should say use appropriate quantities and necessary calculation. Ka value for this acid is given, so all that is given, right? So where do we start? So we can actually start writing the expression for Ka equals, for a weak acid it's like this, H square divided by Ha, right? So then you have the hydrogen ion concentration. You are looking for the acid concentration first of all, because you want to know how many moles you're going to need. So first thing to decide is how much is the acid concentration you're going to need. So rearrange that equation, right? Okay, so let's write that as Ha equals H plus square divided by Ka, right? So we are here now, but we need to work out H plus, which is from here. So H plus would be equals 10 to the power minus 2.19. So from the hydrogen ion concentration, I just substitute in here. Ka is given here, so just put these numbers in. Remember the square on this H plus, then you get this. That is the concentration of the acid you need in the 250 centimeter cube of standard solution, right? So whatever volume that you're making, that's the concentration you're going to need. That will give you a pH of 2.19, but you need to say how much mass is going to be needed. This is going to prepare from solid, right? So way to do that is find the moles that you're going to need for 250 centimeter cube, right? So you know, N equals C times V. We know the concentration that we want, 0.3020, and then the volume is 250 centimeter cube. I divide that by 1000 to get in liters, and then if you do that, that gives us 0.0755, 0.076 moles, right? So that is the number, that's the moles that you need to make up this solution in 250. We need to convert that to grams now. All you need to do, you got the moles, you just have to multiply by the formula mass of 2-hydroxypropanoic acid. So you have that multiplied by mR. Formula mass is 90, and then that will give you the mass of this solid acid that you're going to take. So 6.80 grams. So the student has to take 6.80 grams of this acid, dissolve it in a smaller volume, not straight away 250, and then make it up to 250 in a standard solution. Okay, so that's how you work out and show the quantities involved. I suggest you take a moment to actually go through this, summarize through a mark scheme, look through the mark scheme carefully. So 6.8 gram, that's where we stopped. That has to be dissolved it in distilled water less than 250. So you need to say, oh, you don't have to say that. Then transfer the solution to a 250 volumetric flask and ensure all the solution is washed out from the beaker. So if imagine you're dissolving this in a beaker, and you transfer everything to 250, everything is washed from the beaker. That's a way to prepare standard solutions. And transfer everything into the flask, standard flask, using a funnel. Make the solution up to 250 distilled water, and holding the flask upside down, you thoroughly mix it several times. That gives you this pH solution, standard solution. Okay, pause if you want to have a good look at it. Okay, for a 2-mark question here, so just an equilibrium equation for identify. So 2-hydroxypropanoic acid is slightly stronger acid than butanoic acid. So this is going to be our acid. So this is just an equilibrium equation. Identify the conjugate acid pair. So first of all, let's do the proton transfer from the slightly stronger acid. So that's going to give us CH3 CHOH COO minus plus CH3 CH2 CH2 COOH2. Okay, plus, so don't forget the plus. Okay, that proton has been transferred onto that, right? Then you just have to identify the acid one, go right to the other side and label that as base 1. That has to be acid 2. Go right here and label that as base 2. Done. Okay, so we identified the acid base conjugate pairs. Take a moment to read this buffer question really carefully, where you are actually partially neutralizing the butanoic acid. So pause, read it really carefully. Okay, so I've underlined the main parts. The volume of the butanoic acid you're going to mix and its concentration is given. The volume of the sodium hydroxide is given. So the butanoic acid is going to be in excess for a buffer solution to act. So this is going to produce the salt sodium butanoate. Ka is given. Calculate the pH of sodium hydroxide. So we start off in part 1, it's like 2 marks. So you know what to use is the ionic product of water for this. So what I've done is ionic product of water here, and then rearrange this to get the hydrogen ion concentration. You need to divide that by that point, the concentration of hydroxide ion. Now this is sodium hydroxide, so it's a monoacidic base. You know, NaOH, so one molecule only produces, so make sure that you check that. Okay, sometimes they put CaOH, that will produce 2 ions, 2 hydroxide ions. You have to multiply that by 2. Okay, this time you can just use the concentration as it is of the sodium hydroxide. Okay, then you get the hydrogen ion concentration from this. All you have to do is minus log of this value. That gives you the pH of sodium hydroxide. So that's 13.2. Okay, so to do part 2, we just need to initially understand what's going on here. So you take some of this acid, right? The acid is going to be in excess. That's how buffers work. You're adding some sodium hydroxide. So we need to initially work out the number of moles of butanoic acid and the number of moles of sodium hydroxide used. Then because partially this acid is going to be neutralized by sodium hydroxide. So what we need to understand to work out is how much acid is left after this process. So working out the moles of this N of butanoic acid, that is the volume times the concentration. Volume of the butanoic acid times the concentration. I've converted the volume to liters, and that's this, right? N of sodium hydroxide would be, now we got the volume here and the concentration is given here, of sodium hydroxide is 0.185. Okay, so where are we now? Okay, I've added a few more bits to this. Okay, so the concentration of butanoic acid is that 7.25, which is the moles of the butanoic acid that's left after partially getting neutralized by sodium hydroxide, divide by the volume, and that gives you the concentration of butanoic acid here. Okay, so I need to work that out. Okay, so then the moles of the salt would be the actual moles of the sodium hydroxide. All of that will react. Sodium hydroxide moles, you just have to multiply that with this, which is we already done that here, moles of sodium hydroxide. That gives you 9.25. Got the moles, total volume is this, so we have now the concentration of the conjugate base. Okay, so now we have this expression Ka rearranged to get the H plus by moving that over here, right? Like so, Ha to the numerator, and so we got this expression H plus equals that. We have the Ka value over here of butanoic acid, so use that, times that by the concentration of Ha divided by the concentration of the salt from here. Okay, so you put that in the calculator. Okay, so we have that expression, and just substitute the value and you get that is the hydrogen ion concentration. Now to do this, to do the pH, you just have to do minus log of H plus ion concentration, and then you get this, so minus log of that value. Okay, so take a moment to look through the mark scheme of what we've been discussing in this question here so far. Right, so it's a big question, lots of marks. Okay, so have a look. This is the one that we just did here, part 2. That's the sodium hydroxide pH, 4.93. Is that what we got here? Yeah, 4.93. Okay, so that is what we did just now. Okay, so have a look through. Hopefully this will help in your preparation, and hopefully this helps in your revision. Okay, keep pause whenever you want to. We keep going with some harder problems.